Good morning everybody. Today lecture basically calculation of ESP systems. You have seen from surface to subsurface wellbore and downhole the pump setting area what are the different equipments. So if I draw again ESP system, it will be looking like this. I have one casing. Casing size will be bigger than your tubing size. So casing size will be 758 size normally it will be given in API table. So whenever you want to get any data about casing, what will be like 7 inch, 758 inch, and you cannot get maybe 7.1 inch. Okay, so you have to follow API table. And if you want, let's say for example, if you are a new engineer and you want to design a new pumping systems or artificial lifting system or new casing or tubing, you calculate everything, then you get say your casing size 7.5 inch, and that may not be there in your API table. So in that case you have to check API table what is the nearest casing size, that one is select. Okay, and if you do not use API table, then problem is that you will have to buy many other equipment. For example, ESP system, you have to buy maybe monitoring system. So those things will not get fitted into your system. So you have to follow certain standard so that you can buy or select all the electrical or mechanical equipment accordingly. Okay, so casing size can be 758, 858, or maybe 5, I think 5.5 also one. So different sizes are there, and this will be given as an outer diameter. Okay, if nothing is given, we have to assume this is outer diameter, and if it is specified as inner diameter, is okay. If it is not specified anything, you can assume this is outer diameter. Then inner diameter how to get? Then you have to go to API table, where you will find the inner diameter. Several inner diameter will be there. So based on the criteria, you can take one inner diameter and you can calculate for fluid flow. For tubing also same thing, whether you are calculating your, if your tubing is this one and this is your tubing wall thickness, okay, and you are calculating fluid flow through this area. Okay, so what you have to do, you have to take inner diameter. But if you are trying to take fluid flow through the annulus, this is casing, and fluid flow area is this one. Okay, so if fluid flow area this annular area, then you have to take inner diameter of casing, outer diameter of tubing. Okay, but if you are calculating fluid flow through the tubing, that means inside diameter you have to take. And that's why whenever any casing or tubing diameter will be given, just you have to check it is inner diameter or outer diameter, or what is your flow requirement. Based on that you have to start calculating. And tubing calculation, it will be based on, like say if you want to design tubing, this is not part of this course, but anyway, if you are designing a tubing, one thing is that very thin wall tubing can create, the thin wall tubing will be creating problem because it will be capturing very less amount of stress. Okay, and if you are using thick wall, then your total weight will be increasing, then elongation will be one difficult part. So you have to optimize what will be your optimal size of tubing and thickness also. And tubing diameter, if you are using very narrow diameter, then your piping friction drop will be very high. Or already I explained, I think FLV square by 2GD, you can remember, del P, pressure drop will be very high. Friction factor into length of the pipe, V is fluid velocity. Okay, FLV square by 2GD. Okay, so your pumping power will be requiring very much high amount of pump will be requiring very high amount of electricity. But if you are saying that no sir, I'll be increasing size or diameter of the tubing, then in that case your fluid velocity may be very low. So in that case your fluid sand settlement and other problem can occur. So you have to size your tubing optimally. Okay, optimal size of wall, optimal tubing outer dia, inner dia, you have to calculate. Then you can get optimal production. And if you are sizing wrongly, then your production will get hampered. Your maybe pumping power will be too high requirement, or sand settlement will be too high, so sand will be again creating problem, or maybe fluid is not so high so that you can create multiphase flow. It is phases are getting separated and heavier phase going down and lighter phase like gas is going up. So in that case liquid loading can occur. So you have to calculate the tubing size properly. Okay, and inside again you will have pumping systems such as ESP or SRP or some other pumping systems. Okay, now inside casing there is tubing, and you will have your perforations. Okay, and we are assuming this is your oil and gas zone, and you are perforating this one, and you are getting your production from here. Okay, so from here there will be one casing head, you can remember, then it will be diverted, and there will be Christmas tree. This is a whole mechanical arrangement. And where will be the pump? Pump will be the nearby bottom area, and pump may not be at nearby perforations area, it may be below or up. If it is you are putting pump upper than perforation area, then you have to check how much head available, NPSH. If net positive suction has requirement higher, then pump you have to reduce this, you have to bring down the pump height, then your NPSH will be available, will be increasing. And if you are moving up pump, then NPSH available will be lower. So pump setting depth also you have to check how much pressure is there in your wellbore. Accordingly, you have to check your pump setting depth, and how much pressure it will develop. It will be developing pressure like total hydrostatic head from pump to the surface. Then surface there will be requirement of some piping requirement to reach to separator system. If separator system also requiring certain pressure, then you have to calculate separator pressure plus piping pressure plus some elevation, if there is any elevation or wellhead pressure drop. So those pressure plus frictional pressure drop plus hydrostatic pressure drop, all the pressure you have to calculate, and that much of head pump must be developing. Okay, and pump can be installed in vertical or horizontal condition. A pump can be, for example, you have one horizontal wellbore. Okay, it is going like this. So pump, you can install pump here or you can install here based on your head. And whenever you are calculating your hydrostatic head means true vertical depth you have to calculate. Okay, true vertical depth, actual vertical depth. And what will be your frictional pressure drop? Frictional pressure drop means you have to calculate this length. Okay, this will be giving your frictional pressure drop. So del P friction, just I am giving my own name. It may not be there in your book. Okay, this is true vertical depth. So true vertical depth, it will give hydrostatic pressure P hydro. Okay, and frictional pressure drop it will give, and you will be requiring maybe some friction or losses will be there at the wellhead, and there will be certain pipeline here. Well, choke may be there, one pipe will be there, then it will go to separator. Okay, so that means your pump must deliver certain amount of energy to the fluid so that it will be overcoming all this friction pressure drop, hydrostatic pressure drop, wellhead pressure drop, piping pressure drop, then it will reach to separator. Separator also will be requiring certain amount of pressure. So your ESP will be giving all the power, okay, all the pressure. Again, if you have electrical component means your motor will be here at the bottom right, we discussed. So motor will get power from the surface. Okay, so from here, let's say we are getting more electric cable is coming, it is going to motor. So motor, first it will go to your junction box, right? Junction box to your switch box, VFD controller equipment will be there. Then there will be transformer to your high tension line. Okay, so let's say 11,000 volt you are giving, but you may not be requiring that much of volt. So you have to reduce, step down transformer will be there. So it will be reducing volt 11,000 to maybe 440 or 4,000 volt. Then you have to pass that electricity through junction box or vent box. I already told, vent box means if there is any gas coming from wellbore through the cable, then that gas will be vented out, and that will be connecting your cable, wellbore cable, and your cable coming from your switch box. So those will be connected to your junction box. CTI1 junction box or vent box. This is switch box. Okay, TCCH switch box. This is your transformer. Okay, so whenever you are installing any subsurface electrical submersible pump, so what the things you need to know? You need to know your how much pressure you are generating, what will be your casing size, what will be your tubing size, how much flow rate you are having, what is the fluid property you need, whether sand is coming or not, whether gas is coming or not, gas liquid ratio, sand property you have to know. Then whether it is creating two-phase flow, phase diagram also you should know. Then you have to know how much pressure drop is happening from bottom wellbore to the surface, And again you have to check sand phase completion, how much pressure drawdown is there. If the pressure drop is very high, then maybe NPSH will be creating problem. So if you follow all the lectures whatever I have done, wellbore pressure is there, reservoir pressure is there, reservoir pressure will be lost when it is passing through your reservoir channels, then sand phase completion, some pressure drop will be there, then your fluid is entering into wellbore, that flowing pressure PWF, right, we have written in previous lectures. So flowing pressure you got. Now that pressure if sufficient, then is okay. If it is not sufficient, then you have to give some inducer. So that inducer or small axial pump that will be giving extra pressure to main centrifugal pump or main ESP, and then ESP will be developing all the fluid. Now you are creating two-phase flow, or you have free gas. Because of NPSH, lower NPSH, gas will be coming out from your fluid, so that will be creating problem. Okay, so you must have one gas separator here. Before motor, after motor, one will be gas separator. So gas separator. What will be location of gas separator? Just before pump. It is called intake section. At intake section, there will be one gas separator. So gas separator will contain your inducer also. So that will give some NPSH. And in between gas separator and motor, there will be another equipment. Can you remember? That is called protector. Protector, what is his job? His job is to protect motor, not pump. Okay, so motor will have dielectric fluid and protector will be protecting the motor. Now you got electric cable, electric power came to motor, motor is giving rotation. So on shaft, it will give torque. Shaft is long shaft, it is reaching from motor to protector to your gas separator, then pump. Okay, and it will be connected in many places. It will have radial bearings, many places radial bearings, so that when it is rotating it will not vibrate, and it will have some thrust bearings also, so that if axial load is coming, so axial load should not get transferred to pump, to your gas separator, to your protector, to your motor. Okay, so there must be thrust bearing in many places, so that axial load should not be transferred, because this shaft is designed for your torque only. Okay, torque means power. How it is related? P equals T into omega, torque into rotational speed. So if your speed changing, torque can be changing for the same power. Okay, so formula is P equals T omega. Okay, now if you want to calculate friction or pressure drop, then there will be several charts available, or you can use some approximate formula. Okay, and hydrostatic pressure you can calculate using again correlations, multi-phase correlations are there, single phase correlations are there, you can use for single phase fluid flow. So single phase fluid flow may have different viscosity, oil water viscosity, or emulsion can be created, or if it is having gas bubbles, again there will be another issue, multi-phase will be created, whether it will be separated model you are creating or homogeneous model you are creating. So you can use several softwares available these days, but still you have to know how things are happening. Okay, so some manual calculation you have to do. Let's try to do some first manual calculation here. One problem taken from Guo et al. Book. This is book title is manual ESP manual. No, this is petroleum production engineering. Petroleum production engineering. Okay, so his this is reference book for this course. The problem is that 10,000 feet deep wellbore, 10,000 feet deep. Okay, 10,000 feet wellbore is having 32 degree API, 32 degree API oil. Okay, while gravity is given then with gas oil ratio GOR is given 50 SCF STB. You can remember standard cubic feet. Whenever you are saying standard cubic feet, that means 14.7 psi pressure, 60 degree Fahrenheit. Stock tank barrel means surface condition. STB means stock tank barrel condition. Okay, there will be again the normal condition like 14.7 psi and 60 degree Fahrenheit condition. So gas oil ratio GOR you are measuring, and zero water cut. So WC equals 0. And what is given there? 3-inch tubing. Tubing size 3 inch given. That means this outer diameter is given. Inner diameter is 2.992. And how do you get 2.992? It may be given in the problem, or you have to find some table, API table. From there you can get 2.992, that inner diameter. Okay, because this fluid will be flowing through the pipe. So you need to know this 2.992 inch ID. Okay. Tubing 7-inch casing. So casing size is 7-inch casing. Okay, and tubing size is 3-inch. So casing size 7-inch means outer diameter. Inner diameter will be lower than 7-inch, maybe 6.5 or something. Oil has a formation volume factor 1.25. So BO is given 1.25. Okay, and average viscosity 5. Mu average is given 5 Cp. Okay. Average viscosity is given because from wellbore to the surface, the viscosity changes because of pressure and temperature change. Gas specific gravity is given 0.7. So gamma gas equals 0.7 is given. And the surface and bottom hole temperature again given. Surface temperature given 70 degree Fahrenheit. 70 degree Fahrenheit, because nearby surface temperature lower, and wellbore temperature is higher, 170 degree Fahrenheit. The IPR of the well can be described by the Vogel's model with reservoir pressure 4350 psi. So P reservoir is given 4350 psia absolute, and absolute open flow 15,000. Okay, so if I draw Vogel's IPR curve, it will be looking like this. Okay, this is PWF. You can remember Q flow rate. So AOF, absolute open flow. Absolute open flow is given 15,000 STB per day, stock tank barrel per day. If the well is to be put in production with an ESP to produce liquid 8,000 STB per day, so production rate will be somewhere here, against a flowing wellhead pressure 100 psi. So wellhead pressure is given 100 psi. P wellhead 100 psi. Okay. Determine PSIA, absolute. Determine the required specification for an ESP for this application. Assume the minimum pump suction pressure is 200 psi. So pump suction, P suction is given 200 psi. Okay. To solve this problem, actually we have to formula here. PWFD flowing pressure 0.125 P bar square root of 81 minus 80 QLD divided by K max minus 1, and D pump minimum pump depth. Okay, minimum pump depth equals depth of production interval minus PWF flowing pressure minus P suction pressure 0.433 gamma L. Gamma L is the specific gravity produced production fluid, 1 for fresh water. So here QLD, desirable liquid minimum delivering flow rate. Minimum delivering flow rate QLD is 1.25 divided by 8,000. Okay, 10,000 barrel per day, BBL per day or B per day. Sometime I write B day, sometime BPD, BOPD, the sort of term will be used. So they have written BBL per day, barrel per day. Now QLD is 10,000. Okay. Now well IPR. Well IPR says PWFD equals 0.125 square root of 81 minus 80 QLD divided by Q max divided by Q max minus 1. Okay, now this is giving 0.125, then 4350 square root of 81 minus 80, 8000 minus 8000 divided by 15,000, 15,000 minus 1. Okay, so this value is coming 2820 psi, and minimum pump depth D equals D pump D minus PWF minus P suction divided by 0.433 gamma liquid. So that value, if I put all together, it will be 2997 feet. Okay, so pump depth, where should I write here, bottom left corner, I write pump depth equals 10,000 minus 200 they have given that minimum 200 psi you have to maintain, so 9800 feet. Okay, P suction pressure equals 2823, we have seen, minus 0.433, 0.865, 10,000 minus 9800, so it is giving 2748 psi. Okay, now you can use your pressure using Hegedorn-Brown relationship, but at this moment we are not using that multiphase relationship, rather we are going for simpler one. So we are assuming that pump discharge pressure is 3728 psi. You can use P equals H rho G formula also for simplification. Okay, for simplification, thus required pump pressure is P discharge minus P suction. So 3728 minus 2748 equals 980 psi. So the pump head equals del P by 0.433 equals 980 divided by 0.433. It will give 2263 feet of fresh water. Okay, so this is a very simple problem, formula based problem. Just try to practice this sort of problem. So in exam maybe I can give similar problem, and I will change something so that you have to think and you have to work on that. Now if pump 6000 feet, if one stage gives 60 feet head, so number of stages, required equals 2263 divided by 60, so it will be like 38 stage about. Okay, if it is becoming fraction, let's say 37.5 or something, then you have to take the higher one. You cannot take lower one, otherwise you will not be able to deliver the required pressure. You have to deliver required pressure little bit more than that. That's okay, because there will be several other losses if you are not counting at this moment.